to give you an idea about what we do at ENS, droplet microfluidics. It's mostly related to droplet microfluidics and optofluidics, and this is the techniques that we're using, and actually we're applying them for different topics, spanning from biology. We have a topic with Professor Dominique Fomi, she's here, about interaction of antibiotics and bacteria, and also we have collaboration with Professor Benassa about the optimization and also Professor Sivajan of heat transfer in for cooling batteries and electrical components. But we have other biological topics and also material science. So I will try to give just very quickly about some of the topics as well. So maybe it looks like something that is a chaotic presentation, but we can just open discussion. Okay, so here we have, for instance, we are not using only droplets, and we use droplets also to fabricate microspheres, microcapsules that can serve as building blocks for other materials, for material science, or as microreactors, or as optical resonators, for instance, for biosensing and other applications. So you know that microfluidics is not a new science, it's an old science. Maybe Poiseuille was the first about talking about, it's in French, was defining maybe the microfluidic at that time. So what changed, and nature is doing this since ages, but what changes actually during the last decades is the technique that we are using, to develop devices, and the modulation and all the design that we can do. So I'm not going through the details, you know all this detail now. Basically, microfluidics or single-phase microfluidics, you know, because of the low Reynolds numbers, the flow is mainly laminar. So if we want to make reactions, this may be a little bit complicated, because if you want to mix reactors, only diffusion will be the main driving force. And if you want to activate to get it faster, then probably you need to go further. But before further using droplets. But just before, what makes the magic of microfluidics is that you can use really have nice application like sorting just with a micro channel. You can sort particles depending versus their size very easily using the H filter, for instance, the very known H filter, and this is based on advection, between competition between diffusion and advection. So this can be done nicely. You can sort very easily particles, for instance, or protein. You can also sort particles actively by applying forces, and these are, we have some talking about electrophoresis, magnetophoresis, and also could be also electrophoresis. For instance, you can, a nice paper a few years ago, almost already 10 years ago, about the sorting of cancer cell, tumor cell, sorting CTCs using magnetic forces, using magnetic nanoparticles that are targeting some tumor cells. And this can be done easily, because this, for instance, here you can see two images. This is images that we did during an internship of our students, just incorporating magnetic nanoparticles, and did you see without applying any magnetic field, when we split the droplets in two parts, the magnetic nanoparticles are evenly distributed in the two droplets, but if you put a magnet just beside one of the branch, then you can really sort it very nicely. So you imagine that the magnet is set here from this side. So this is really just like one-shot experiment and very quickly. As I said earlier, so what makes a little bit one of the drawbacks of single-phase microfluidics is that it is the mixing. And for this droplets microfluidics is really good. You can see this is not our video, but it just to illustrate a droplet mixing two droplets with the state, and the merging occurs few milliseconds after the merging. So and this is because of the recirculation of inside and around the droplets. What is also very interesting with droplets microfluidics is that you can produce and control the size and content of droplets very nicely, and every droplet can be used as microreactors, either for biological assays, for chemical reaction, for physical processes, and so on. And you gain a lot of sensitivity during and also time, due to the high ratio of surface over volume of the droplets. Droplet size is about few 10 of micrometers, that is picoliters typically. So what we do in the lab, we develop that's using several strategies. For instance, so this mixing. So this is the laminar flow. You can see here we merge two fluids, two components to induce a biological reaction here. But you can also study single process in single droplet that may be trapped in microwaves. For instance, here. This experiment was done here to use these micro droplets as optical microresonators, and these are 100 micron, and the drops are trapped, and they can remain there as long as we wish for long-term studies. What we do also is the coupling between electrical active how to say that. Field or voltage, actuation. I was looking for the word actuation. Actually, is that you can use this electrical field to inject some reactant in the micro droplets. Here I have already some droplets that are made previously here in this branch, and then you can inject by applying electrical field with the chosen frequency and amplitude. You can inject some quantity here that are even in femtoliters quantity in these picoliter droplets. To illustrate this, for instance, here, if you don't apply the electrical field, there is no merging of the drops, because this is just making new drops and that make merging with the other one. But if you apply the electrical field, you see this in this solution here. You have some particles, could be bacteria, it could be other magnetic or whatever, and then when you apply the electrical field, you can really precisely inject this nanoparticle, microparticles inside the drops. Electrical field can also be used to make droplets also by splitting the flow, laminar flow. You can split it here, for instance, and we published this 10 years ago. Just turn off the electric field, this is AC field, and then turn on, and then you can control the size. And there were some nice, very nice results with that. We can study what happens in the droplets versus time, of course. And for this we developed. We have an optofluidic platform. So people who are interested to visit our platform, we can organize a visit, as I discussed during the lunch, maybe in two groups to avoid, so we can do that. So what we have here is that to analyze optically the content of droplets using lasers and detectors. And so for this we have every droplet is analyzed, and because of the high speed and the high frequency, typically we're producing 1,000 droplets per second. So, and we can follow that in real time. So analyze the profile of these peaks that give us information about what's happening inside the droplets, but also around the droplets, with an interaction with the surrounding. We can encapsulate cells. This was done long time ago, but just again to illustrate that you can analyze what's happening. For instance, in this droplet, there was some cells that was mixed with some enzymes, and this enzyme is enhancing this reaction, metabolic reaction, that is a beta-galactosidase. This is enzyme, and this metabolized this compound. When this sugar is metabolized, it liberates a fluorescein molecule that we can detect, for instance, in real time. And this gives you an idea about what's happening in the cell in the real time to follow enzymatic reactions, for instance. Also, which is maybe of interest of the topic of our workshop, is that we can produce also some microfluidic devices that can enhance mechanical solicitation stresses on wells, the same wells that you showed earlier, that you can put cells inside, and then you can undergo, for instance, just with the pneumatic solicitation, you can study the effect of this mechanical solicitation on the culture of the cells. So you can choose the different. So here we compress this way, the other we compress this way, and so this was the topic of M2 research thesis of Nahid, and he continued the PhD, not continue on this topic, but another topic. So we studied. But one other topic also is that Looming is a linear light and matter interaction lab. So we developed, for instance, for this optical technique that allows us to control the merging of two droplets, and this is very important. For instance, this was induced by collaboration with biologists from ENS. They were interested here. It's listed here. They were interested to follow the mechanism, to understand the mechanism of compaction of chromatin of DNA. That is, this process is very fast, and this can be controlled by proteins. And as soon as they mix the proteins and the chromatin, the DNA is just compacted or uncompact very quickly, and because it happens probably in below the milliseconds time scale. And the idea was here, okay, why not to control the merging of two droplets containing DNA and these proteins, and then to follow exactly from time zero this merging. So we started to collaborate with chemists from ENS also. That allows us to synthesize a surfactant, because droplets need to be stabilized by surfactant in order to avoid merging. And these surfactants are sensitive to light. So we illuminate, so I don't know if it will be clear here, but we are shining with a laser, pulse laser here. It will start here, so we see that the spot, and we can measure remotely exactly what we want to follow the. Unfortunately, we didn't go further in this project, with at least for the biological application, because we noticed after that the merging is also limited by the diffusion of surfactant at this time scale. In microfluidics at the micro scale, diffusion is really very important, as you know. So what happens here is that the shortest time that we reach with this merging with the laser was sub-second, not millisecond. The target was millisecond, and this millisecond time scale was very hard to achieve, because actually what happens is that as soon as you eliminate the surfactant or the droplets with the laser, so you deplete the layer of surfactant that is around the droplets. But as soon as you deplete, other molecules come very quickly to stabilize again the droplets. And that's why you need to go very, very fast which or to eliminate a larger portion, but the idea was to be localized on droplets. So the idea is not to merge everything, but just to be localized. But it was very interesting. For instance, by comparing the limit of our merging, we could deduce, for instance, the diffusion coefficient of this surfactant in this oil, because we put the surfactant in the oil. So we can follow optically actually what happens in, as you understand, what happens around the droplets. For instance, we could use this surfactant could be a charged surfactant, which is one carrying negative charge around the droplets, and then if we put some probes like rhodamine B, for instance, that's carrying charge in it, then we can monitor the interaction between the drops, between the dye and the surfactant, which is around the droplet surface. And this, for instance, because of when you have making a drop flowing in its microchannel, you have streaming effect. That is circulation line that I bring in the surfactant from the front and getting them at the rear of the drops because of this circulation, and they cannot enter the drops because they stay at the rear. And this means that you introduce a gradient of surfactant around the drop, making a gradient of surface tension. And because of this surfactant is charged, so you can attract more fluorescent molecules, and you can visualize that. So you can see here, for instance, by increasing the velocity, you can see that you gather more and more dye molecules because you have more and more charged surfactant at the rear of the drop. So, and this is very interesting because you really can monitor what's happening around the drop. We could, for instance, analyze the shape depending on the surface, on the surfactant, versus the flow, velocity, and so on. And also we did some testing by changing the pH. For instance, and we see changes happening. So I can discuss this. By the way, some other questions that arise from this result are not solved yet because for us it's not very intuitive as a result. So I can switch from the droplets to the solid microspheres, because as these droplets can serve as also reactors to make some highly monodispersed and controlled microspheres that you can manipulate, because droplets, they should be stabilized. And these are solid. So we studied Chishan, which is here. He is defending his PhD in 2 months, less than 2 months now. On silica, for instance, we're using condensing silica precursors to make silica microspheres with controlled porosity. And we studied the mechanism, for instance, how these microspheres are formed depending on the concentration of the precursor that you put, and there are different factors that enters here, like the co-surfactant that you add in the micro droplets, the concentration of the precursors, the size of the droplets. Also, all these parameters are very important, and you can have, for instance, you can have kind of nice monodispersed microspheres which come directly from one droplet, but we also see that for other conditions you can induce some blibbing of these micro droplets to induce smaller micro droplets, and even in 2 daughters, 3 daughters, and so on. And we also, for instance, by following the kinetics of condensation of this microspheres, we could deduce a mechanism of this formation here, that was published later. Another material that we also use besides silica is that we wondered what happens if now, instead of using just silica, using nanoparticles that have like zinc oxide, for instance, or titanium oxide, that have applications in photovoltaics and photocatalysis. What is interesting with this kind of nanoparticles is that they have electrical dipole which due to the organization of the materials of the zinc and oxygen or titanium oxygen. So this conferred to the particles an electrical dipole, and then it was interesting to see how these nanoparticles that behave as have dipoles orient at the surface of the droplets while the droplet is condensing. And this was very interesting because in this case, besides we produce, for instance, here some kind of polar droplets. Though they are still droplets, they are varying a macroscopic electrical dipole that induce a square organization, well organized, and which expand over micrometers, even millimeters, on our sample. And this is due, actually what happens is because of spherical symmetry, basically this particle should not be polar, but the polarity arises from actually this streaming effect that, as I said, gathers more molecule at the surface of the wheel than in the flow. Thus we create asymmetry driven by the hydrodynamic flow, and this makes this microparticle polar. And we show that, for instance, also by analyzing the shape of the optical peaks that comes from the droplets when they are flowing in the microchannels. And also you can now, for instance, here you can apply, since these nanoparticle organize on the surface of the microsphere, these are microcapsules. This is they are hollow microspheres. And you can apply electrical field, for instance, here you can see these kind two population. Actually, the small one are the microcapsules, and this one, they come from after the application of the electrical field. They just like pop